Serkan from İzmir High Technology Institute, and I am also involved in the PhD program of the university. I will talk to you about the composite materials absorbing the radar waves. I would like to thank the organizing committee of TURK KOMPOZIT 2015, and of course thank you, the audience, for coming. This is a study about my my master's degree thesis, and it was supported by KOSGEB. I would like to thank Professor Metin Tanoğlu, Professor Lütfi Özüver, and I would like to thank Mutlu Devran Yaman from the physics department. We have been cooperating. Bertan informed you about that, but I also would like to inform you shortly the devices and the production techniques have been enhanced. We have a lab discovering many techniques, and we used the infrastructure of this lab, and I'm really lucky. I feel really lucky to work in such a place. The content of my presentation, of course, radar and radar absorbing will be touched on, and then radar absorbing materials and structures will be mentioned. The literature, what are the studies in the literature, and in addition to the studies in the literature, what is our motivation? Why did we launch such a study? Our targets, experimental studies, results, and assessments. What is radar? Radio detection and ranging. It's shortened to radar, and it was first used during Second World War by Americans. So high-frequency radio waves are used to detect the position, speed, and the shape of the good or a particle. You can see it in the animation down. We send an electromagnetic wave, and it just is reflected, and its reflection differs according to the speed and the size and the shape of the and position of the item, and we can detect everything thanks to the radar system. Electromagnetic wave. Electromagnetic spectrum is quite wide. Where are we interested? I will try to inform you about that. Electromagnetic spectrum. Microwave is what we are interested in, because radar systems and satellite communication systems work on this band. Well, on visible light here, for instance, there is almost the area that we mention is around 10 to the power of 9 or 10 to the power of 11. Microwaves are divided into bands, and we work on 2 to 18 gigahertz. SCQ bands are the bands that we are working on, I can say. When we say radar wave absorption, of course, electromagnetic wave is sent, and we are trying to prevent reflection. You can absorb the energy of the radar, or you can just skip it to somewhere else. There are different methods. Shaping is the first method, and there are a little bit examples here. There's a frigate here, and this is the aircraft. Compared to the regular aircrafts, these aircrafts have very little edges, because in geometry, if the radar touches those edges, it reflects back to any places, and you can get detected. In order to minimize that, geometry is to be flawless. Of course, there are certain limits. because you're a vehicle there, physically there, I mean, you cannot just disappear. This is where you need the absorption material. The absorption materials have dielectric conductivity and magnetic permeability and conductivity. The electric absorbers are based on carbon graphite, short carbon fibers, carbon nanotubes, and carbon nanofibers can be samples here. Magnetic absorbers are metal based. They are iron oxide, nickel, and zinc, cobalt, and manganese. Or ferromagnetics like carbonyl iron or barium hexaferrite can be mentioned. What about the structures? In addition to the materials, well, we have to use the materials available wisely, actually, and we can increase the absorption level by wisely using the materials. Dilembach layer can be mentioned. This is a simple structure. There is a metal at the end. It's a reflective material. Electromagnetic wave that you send returns, reflects from here. And in between there is lossy material. The material that will enable the loss. It can be a filling material. It can be any of the materials that I mentioned before. And of course there is certain magnetic properties over here, and they can be different in design, and there is thickness over here, and thickness is very much important. This is the most simplest structure. Salisbury screen is a resistive screen. It creates a resistive layer. An electromagnetic wave coming is just skipped back. It's just bounced back. And thanks to the absorbers, you can absorb it more. Well, green gas impact or ozone layer can be samples. The atmosphere being available all the time. And another developed absorber is Yauman absorbers. They have additional resistances and the number of layers increase. What does that enable? I would like to share a graphic with you. Well, this is the frequency on the bottom line. The radar frequencies are used from 0 to 20, and this is the reflected power. It's a decibel logarithmic graphic. 10 decibel equals to 90% of loss, and 20 equals to 99% of loss. And if a single sheath is used, you see how much loss is achieved. If we achieve 20, we can only have a short or bandwidth, and the absorption will only occur at that bandwidth. But as the number of sheets, resistive sheets, layers increase, their endpoints increase, and the 20 decibel bandwidth increases incredibly, and this was one of the targets of the project. The literature, studies in the literature. There are two studies that I would like to mention here. Micheli et al. Conducted a study, and within epoxy matrix they put the electric material. Graphite and carbon nanofibers are used at different levels, and they are put in on top of each other, like a series, and at different percentiles, different materials are used to enlarge the bandwidth, and this is enabled. Another study includes the resistive sheath on PET film. a very thin metal coating is done for resistance, and polycarbonate structure is integrated with that. And it has a different frequency interval from 40 to 70, and it enables an important absorption. These are already done. And why are we doing it? Because these studies have been especially on radar absorption. But what do we want here? The materials that we produce should be functional as well. We want them to carry a burden. Here, composite materials are on the stage. Let me explain you our motivations. For instance, wind turbines. It's not only the military purposes or warrior aircrafts, but wind turbines can be used for that reason, and this is a radar system to measure the temperature, and this is a wind turbine which are mostly installed on hills. This is a normal view, and there's a cloud here. Cloud is detected, but air radar is here, and the wind turbine farm is over here. There is no cloud here normally, but because of the sound wind turbines create, it shows as if there is something here. It misinforms us. How can we prevent it? The radar wave can be absorbed by the wind turbines. Of course, it's not for the atmospheric measurements, it's true for military purposes. Think of that. If there is a noise here, you cannot see any object coming from here, and this noise has to be dealt with by absorption. As you know, the wind turbine panels are created, the wings are created with the composite materials, and we try to modify them. Well, we can also use it for electromagnetic shielding. There might be some areas which are to be banned from mobile phones. The electric signals can be seized. So the radar is absorbing the waves, and at the same time it can have a structural performance, and it can be applied easily to the vehicles and structures without changing any processes. Almost you can add on a tiny thing and it can be usable. Our targets, as I said before, our aim is to create layered polymeric composites which can absorb the radar wave. 218 gigahertz have been picked as the frequency interval, while in literature 8, 12 or 48 have been picked with a single band. They are working on a single band, but here we have a wider interval as a target. 10 decibel loss of reflection is aimed, and 90% of absorption is required for that. The genetical algorithm, the optimization is done. Well, it's one of the targets actually, and the modifications conducted, how will they impact the mechanical properties? We want to detect that. In modeling, I won't go into details. There are similar structures, especially the Allenbach layer. It's the same. Transmission theory is mimicked here. Between the surfaces, impedance values are important, and they have to be in harmony with the moving wave. And when these impedance values are extracted, it leads to reflection loss. Thanks to the equations, we can have a result. And there are some variables here, thickness or the type of the absorbing material. So based on material, it can be dielectric or it can be magnetic conductive. Salisbury screen, there is a tiny modification here, because we have to get closer to reality. We have continuously reinforced composites, and on the outer part, we have an epoxy layer. It's not a full resistance, and epoxy has our filling material. Therefore, we have a 4-gap layer instead of the resistance layer, and it is thick to a certain point. These are variables of the design, and we put them in the genetic algorithm. Yauman absorber, the number of the resistance increased here. The number of the resistive sheets increased here, and we used all of this in genetic algorithm optimization, and we have a 4-gap layer. Looking at the experimental studies of core composite based radar absorbing materials are either glass fiber or epoxy. Ferromagnetic absorbers, they are carbonyl iron by 25% of 25% of them are carbonyl iron, and for resistive layers we have metal coated glass fiber layers. And here you can see the regular glass fiber and metal coated glass fiber. Well, it's 10 to 15 nanometers, and it's not quite visible by eye alone, by naked eye. Here the pressure alternating can be done. We pressurize the material in closed mold, and we produce the desired model. As I said, I use glass as a reinforcement, as matrix. Epoxy is used, and its momentum is L160. As a filler, we use carbonyl iron. The curing, it has been cured in room temperature for 16 hours, and post-curing 24 hours at 80 degrees Celsius. You can see the structures formed here. They are metal sheets, flat metals, and A is just a sample. It doesn't have a filling material or resistive layer, but on the other ones there is carbonyl. The carbonyl here gives the color. Experimental studies for mechanical properties. Of course, we had mechanical studies, not only pulling but pushing tests have been done. The breaking and fracture and cracking tests have been done as well. It actually fits the standards. The tests fit the standards, and at the same time, impact endurance tests have been realized, and fiber reinforcement volume rates have been detected. Measurement of loss of reflection. We have the grid mechanism here. We have the antenna, and it was done between 2 to 18 gigahertz frequencies. Results. Let me talk about the structures. We have 5 structures, and the number of layers, 8 in all of them. The configuration can be seen here, and you can see the resistive sheet. The fibers are here, and mid-plane is symmetrical. On the first one, it's a reference sample. There is no add-on, no additives. And on B, we have carbonyl iron, and it is equaling the Dallenbach layer. On C, it's carbonyl iron, and we have 1 metal coated fiber. On D, there are 2 metal coated fibers, and on E, there are 3 metal coated fibers. Reinforcement volume rates. Of course, they impact the mechanical properties very much. Therefore, we detect them and we compare them. 36 to 44% of difference occurs. It might be because of the variation technique. We have to think of them. We have to consider them. I will talk about them soon. Microstructure, SEM graphics. backscattering electron method is used, and they create contrast differences based on number of atoms. And of course, the number of atoms within the iron is high. Therefore, carbonyl iron can be detected within the structure as white dots, and glass fiber can be seen easily. And there is 0 to 90 direction glass fibers here. Here, carbonyl iron is not distributed homogeneously in a homogeneous fashion, and that has an impact on our results. Pull-out properties on endurance strength and on module, there are losses around 20%. Our reference sample is shown as A, but on the other samples there are losses. Maybe we can think that the variation might be similar, but the difference is an observable one, a big one. Carbonyl iron was added here. This might be the reason, because as the number of resistive layer increases, there is no decrease, but when carbonyl iron is added, there is a decrease. So this is not only true for pull-out, but in the impact test there is a 30% of loss together with the add of the carbonyl iron. Epoxy surface interaction and epoxy might lead to that. Actually, mechanically there might be a gap, and our mechanical properties might be impacted because of that. The simulation results and reflection measurements. The interrupted lines are the experimental results, and the big black one is the B. D, I think, is the highest sample, and the straight lines are the models. 6 gigahertz is the deep for the model, but with the experimental study we couldn't see it. But there is a similar pattern other than that. There are some reasons behind that. But before that, after the first party, we had Mutlu to work on that. We increased the number of layers. It was 8 normally, but we increased the number of layers to 16. We use epoxy again. And he adds one other resistive layers. I used 3 and he used 4 maximum. And our fillers are 25% same for both of us. And the modeling is similar. The result. At first, there is 15 decibel was not possible to see, but later we have 20 decibels. Why? Because of the thickness. Thicknesses were very finely tuned. But of course there are differences between models and experimental studies. Why? Because with models we think of our layer as in continuous material, but on unidirectional fibers it might be continuous at 50 degrees, but at 90 degrees they are not continuous. This might be the reason. Microstructure are not distributed in a homogeneous fashion because they have a different density. Therefore, there might be different particle sizes required, or a different modification might be used. The resistance layers distance between each other have to be similar. They have to be equal. And lastly, the metal plate on the last part should be perfectly adhered. Sometimes there might be gaps, and this will have an impact on the result. As a result, Well, radar wave absorbing materials and structures have been created, and the metal coated fibers and carbonyl iron has been used to absorb the radar wave. The resistive layers were added and bandwidth is increased thanks to that. The additives have an impact on mechanical properties, and there are differences between simulation and measurement, and I explained why. Thank you very much for your attention. This study was supported by COSGAP, the supportive institution for the small and medium-sized enterprises. Thank you.